We now begin to discuss some of the requirements that might be placed on a battery management system. And you'll notice the numbering scheme here of number requirement 1, and you go back to the previous topic, and that has to do with sensing and high voltage control. So we're going to look at the first 3 sensing requirements in this topic, and then in a later topic we will complete those. So the first requirement is for battery pack sensing is the ability to sense voltage. And this is important. All cell voltages are measured in a lithium-ion battery pack. And that's quite different from other chemistries. So for lead acid, you've got your 12-volt battery, which you know is 6 2-volt lead acid cells in series, and we never measure the 2-volt cells because we don't need to in that case. The technology is leaky enough, inefficient enough, that it also has the ability to withstand overcharge enough that we can in fact get away with not measuring all the individual voltages because we can force the battery pack into a stable situation by so-called float charging. That's just one example. NiCad batteries for hybrid electric, not NiCad, nickel metal hydride batteries are often not individually sensed either because there's just so many of them, and they also have a little bit of more robustness than lithium-ion cells to overcharge. But lithium-ion cells are so efficient coulomically that if you put an electron in, you're going to get an electron out, plus or minus almost nothing. So they're very sensitive to overcharge. If I put too many electrons in, I'm going to have self-heating, and I'm going to have serious problems. So we measure for safety. I don't want to overcharge the cells. They lead to thermal runaway. This here is an actual photograph of a cell that caught fire at Sandia National Lab when they were testing it. They were overcharging it on purpose to see what would happen, and this is what happened. Cells on fire bad. But more than safety, we use it as an indicator of, are the cells balanced? Do they have roughly the same state of charge and internal states? And most state of charge and state of health estimation algorithms require cell voltage measurements in order to operate. If I've got cells in parallel, they share a common voltage, so I can't actually measure individual voltages, they're the same. But if I have cells in series, they could have different voltages. So when we say all cell voltages are measured, we're really saying all series cell voltages are measured in a lithium-ion battery pack, and there can be a lot. Usually around 80 to 100 lithium-ion battery cells in series in a battery pack. And that would be a lot of voltage measuring chips. So a voltage measuring chip is called an analog to digital converter, an A to D, and I would need a lot of those. Because of that, the chip designers are coming up with special devices, special chipsets to aid the high voltage battery management system design. And these devices combine a lot of functionality onto one chip that you would put in your design as opposed to many chips. These chips are dumb in the sense that they are really measurement devices. They're not computation devices. You can't put your own program onto this chip and have it do special things, but you can command it to make measurements. So it's a measurement device. And often these chips are placed in the cell modules themselves, close to the cells, and maybe far away from the battery management system master controller. So the master controller does all the high-cost computational processing, but the measurement is done locally and communicated back somehow. That's not always true. Sometimes there are wires from every cell going back to the master unit, and these measurement chips are not proximate to the cell, and they are proximate to the master unit instead. That introduces some concerns with noise injection with long wires that you have to be concerned about, but it's a design issue, and what are the trade-offs, and how do you really want to do it? So these special chips implement a difficult task of very accurate voltage sensing where there's high common mode rejection, which basically is the DC bias from cell to cell. You know, the bottom cell in the battery pack starts at 0 volts, but the top cell starts near 300 volts. And I have to be able to deal with these large voltage differences in my chipset somehow. And we want fast response in a high electromagnetic interference or EMI environment, a high heat environment, a high vibration environment. All of these are typical of the automotive application. So this is why it's valuable to have special purpose chips that do this. Some expert analog circuit designers have come up with a solution so that you don't have to reinvent their solution. You just use their chip to do this job. And anymore, there are standards that are coming out that have to do with fault tolerance and safety aspects, and these requirements are moving in the direction of more and more redundancy in the battery pack. So you might need several different ways to compute state of charge as a check against each other. And there are sometimes requirements for redundant electronics also, which means that you place these chips in parallel, so if one of them fails, the other one will either still work or at least be able to notify you that there's a very different reading of cell voltage between two chips of the same voltage, so something went wrong. And then you can look at that to try to determine what to do about it. There are a number of companies in the marketplace that make chipsets, and the last time I checked, there were circuits from Analog Devices and Atmel and Intersil and Maxim and O2 Micro and TI. We're going to look at the schematic, well not schematic, but high-level overview of one that's designed by Linear Technology. And that's the one we're most familiar with. Linear Technology has a design center in Colorado Springs, which is where we're located, and we have a relationship with them. They've been very generous to us in donating things to our laboratory and helping to support. So I'm really not allowed to plug one above the other here, but I do mention that that they do have a good product in our experience. This is the one that we've actually used in our own lab. So this is just an example, though. So this is a device, LTC, Linear Technology Corporation, 6803. That's just the part number. They had a 6801, then the next design iteration was 6802, now it's 6803, and last I checked, I believe there's already a 6804 out, and no doubt there's a whole product line that is planned. So each one improves on the previous generation in terms of accuracy and noise rejection and capability and so forth. A single chip is able to measure cell voltages of up to 12 cells. So if you had a module with 12 cells in series, you would have one of these chips being able to read all of the voltages in that module. And then they have a very clever way of communicating from chip to chip that is quite noise immune, and it doesn't require external isolation circuitry, that allows you to stack up to 12 of these in series so that you can monitor up to 120 cells in series. So that's roughly a 500 volt battery pack with lithium ion cells, and that's about as much as most people would ever want to do, at least at present. Inside of the chip, you can see that the cell is connected externally, and the connections go to an analog multiplexer, which go to a 12-bit sigma delta delta sigma analog to digital converter, which is one way of doing analog to digital conversion. And there's registers that store the voltages, and there's a voltage reference that's used to control the converter and so forth. And then the serial data is communicated from chip to chip to chip, and then ultimately back to your BMS. So your BMS can tell the chip when to make the measurements, and it can get the measurements back. And it works pretty flawlessly. There's also external connections for measuring temperature. As listed here, we can measure one external temperature using a thermistor. We'll talk about thermistors in the next section. But using some external circuitry, they have the ability of measuring up to 4 different temperatures. So not 12, but 4, so you can choose your locations wisely in your battery module where you want to measure temperatures. Also, you can see this resistor here with a transistor switch. Basically, you can see if that switch is turned on, the resistor is in parallel to this cell, and that's going to drain some charge out of this cell, which seems maybe a silly thing to do, but in fact that's one way that we can balance cells. So if somehow or other one cell has too high a state of charge compared to the others, I turn that switch on and it drains some charge, and then the battery pack is balanced. We'll talk more about that in Chapter 5, I think, of some balancing methods. And this chip shows that it's capable of turning on and off balancers. And this is called passive balancing when I use a resistor. There's other types called active balancing, and this chip can also control active balancers using that output also with external circuitry. So again, I like Linear because they've been very generous with us, but I can't endorse one company above another. So I use this as an example to show you some kinds of things you might expect to see on a chip that measures voltages for a battery stack. I have some words on the next page. I think we've talked about them. This particular chip monitors 12 cells in series, 120 cells in a pack. We have communications that are daisy-chained from part to part. We can have internal or external cell equalization circuitry. I didn't mention this, that the chip can actually be powered by the module of cells, which is kind of nice, so I don't have to route some power lines to it, although it can be powered externally as well if that's your preference. And we can measure up to 4 different temperatures per chip. Here are some things you might consider when you're selecting a voltage measuring chip. How many cells can each circuit monitor? How many cells total can be monitored? And how basically then compare those to your requirements for your battery pack? Is this a good solution to your requirements? Does the chip support balancing, or is that something you'll have to add yourself? What is the accuracy? Is that sufficient for your application, or do you need more? How many temperature measurements can it make compared to how many you are required to make? How much wiring? This is not a trivial consideration. Wires are expensive. It doesn't seem like it, but they are, and they break, and so forth. Connectors are really what make the wire expensive. Wire itself isn't that bad, but how many wires are required? And if you can cut the wiring down, you're going to make your solution most likely much more robust and less expensive. Another thing which is subtle is what is the availability of this chipset? So if you are General Motors, maybe this doesn't matter because any supplier is going to build the chip for you because you have a big enough volume. But if you're doing something in a small volume, can you go to your electronics website and order this chip, or to the company and order it? Or is it really something that's kind of vaporware, doesn't really exist? And so that's just something I caution you to be careful of, because not every vendor that advertises a part actually has a part available for sale on small volume. What is the cost of the solution per cell? Because different solutions handle different number of cells. So either per cell or the total cost required for your application is something that you should consider also. So that's enough on voltage. We will assume from now on that we have the ability to measure the voltages of every cell. Now we move on to looking at the next sensing requirement, which has to do with sensing battery temperature. We saw in 5710 that the battery cell characteristics, and therefore the pack characteristics, are strong functions of temperature. Things tend to be faster at warm temperature and slower at cold temperature, which basically means you've got high resistance at cold temperature and low resistance at warm temperature and so forth. So they just operate differently. So if I need to manage a battery pack, I need to be able to understand how I expect it to work, and that depends on temperature. Also, cell degradation rates are strong functions of temperature. For the most part, high temperatures cause higher degradation rates, just because chemical reactions tend to speed up at high temperatures. However, cold temperatures can also be a problem because they slow down certain things. For example, they slow down the ability of lithium to intercalate into the negative electrode materials. So if I try charging a battery cell at low temperature, the negative electrode materials may not be able to accept lithium at the rate at which I require it to do so. And that results in forcing current through a cell, and if the lithium isn't going into the particles, it's going somewhere else, and it's doing something called lithium plating, and I never get that capacity back. It's really destructive to do lithium plating. We talk about that very briefly in Chapter 7 of this course. So that means we don't charge at low temperature being 0 degrees Celsius or below. There's some room for fudge in that. Maybe you change the temperature a little bit, but roughly speaking, we're very careful when we're charging at low temperature so we avoid lithium plating. We want to control the thermal management system to keep the temperature in a safe region. And a talk I once heard by someone who was very much involved in the Chevy Volt battery design process said, she said, the battery is the diva of the vehicle. And I just love that statement, but it's really true. If the battery isn't happy, then the vehicle isn't happy. When is the battery comfortable? A rule of thumb for temperature is if you are comfortable yourself, then the battery is comfortable. So temperatures kind of around 20 degrees Celsius plus or minus 5 or 10 degrees are pretty good. Anything much outside that range is not the best operating range for the battery system. So if you have a plug-in capability, then by all means control the temperature while you're plugged in to warm it up or cool it down. If you don't have a plug-in capability, then you have to be a little bit more careful because you have to use battery energy to control the temperature. And so there's a trade-off there between how much you heat it and cool it. But we certainly need to keep the battery system safe, and if we want excellent performance as well, we want to have even narrower temperature bounds. Also, measuring temperature allows us in some cases to have an indicator that something is seriously wrong, like a cell failure. If a temperature changes, if the temperature increases quite rapidly, that might indicate that I've got some kind of a short circuit or a soft short circuit inside of a cell that's causing this temperature increase, and I need to be careful and watch out. Now, this isn't quite as useful as you'd hope, because usually by the time you measure the high temperature, it's already too late. But there may be some situations where it's still good to be able to know that. We would love to be able to measure the internal temperature of a cell right inside the package, but at the moment, nobody manufactures cells with internal temperature sensing, and I think it's unlikely that they will do so. To put electronics inside of a cell requires a lot of industrial engineering to get it right, and it's quite expensive. You have to make sure that there's no short-circuiting with the wires of your sensor. You have to ensure that the whole package is sealed, so there's no leakage of battery stuff outside and so forth. It's just really very complicated and expensive. So usually, always, we measure temperature outside of a cell, sometimes right at the surface of the cell, but sometimes not. So we saw the linear technology voltage measurement part could measure up to 4 temperatures per 12 cells. That means that we would need a thermal model for a battery pack that converted temperature readings at one measurement point to predicted temperatures at different points inside of the module or pack. So we place sensors external to one or more cells, and we calibrate the internal temperatures based on our model. And that turns out to actually work pretty well. So we don't need a whole lot of temperature sensors, but we do need some. There are two basic ways electronically of measuring temperature. Any way we do it somehow has to produce a voltage signal. We have to convert a temperature into a voltage, and that voltage is measured using an analog to digital converter circuit. So there's two basic ways of producing a voltage from a temperature. One of them uses a technology called a thermocouple, which is very trivial. It's just two wires of different metals that are wrapped together to make a metal-metal junction, and it forms essentially, electrochemically, a battery, an extremely low voltage battery. Just these two voltages together have some kind of potential across them, and that potential changes with temperature. And the potential is usually very, very small, I forget, but it's less than millivolts. I think it's a very, very small voltage, but if I can amplify that small voltage and measure it, then I can infer what the temperature is from that. If you read about thermocouples, you'll read about cold junction compensation, which allows us to calibrate the measurement. And thermocouple measurements, while they're quite accurate, and they change, the measurement changes quickly if the temperature changes quickly. There's not a lot of thermal momentum with a thermocouple. It has rapid response. Because the voltages are so low, they're very easily influenced by noise and so forth, and this requirement for the compensation also makes the circuitry more complicated. So thermocouples are probably best suited for laboratory-controlled tests. In my experience, products that measure temperature instead use thermistors. This is just a special kind of resistor, and all resistors have a resistance value that do change with temperature, but a thermistor uses materials that are specially selected to change a lot with temperature. So the resistance is a very strong function of temperature with a thermistor, rather than with a regular resistor you try to choose materials so that the resistance is a very weak function of temperature. Thermistors can either be negative temperature coefficient or positive temperature coefficient. NTC means that the resistance goes down when temperature goes up, so they change in negative directions of each other. Positive temperature coefficient means that the resistance changes in the same direction as temperature. Either one could be used. And basically then we have to measure resistance. We have to we're changing, we want to measure temperature. We have a device that changes resistance when temperature changes. So if I measure resistance, that lets me know what the temperature is. So now I need a way of measuring resistance. And there's two main ways used to measure resistance. One, for super accurate high precision requirements, you can use something called a Wheatstone bridge. I don't know anyone who uses that in a product, but it's kind of a cool idea, so look it up if you don't know what it is. Or a simple voltage divider. And a voltage divider is a circuit that looks like this. I might put, say, 5 volts there, and I might ground that, and I measure this voltage. And if that's R1 and that's R2, then the voltage equals R2 over R1 plus R2, all times the overall voltage, in this case 5 volts. So if one of these resistances is constant but the other resistance changes, then I have a voltage that depends on the changing resistance. So I could put the thermistor either as R1 or R2, either one but not both, and then I put a known fixed resistance as the other one, and that allows me to infer the resistance from the voltage. So from voltage, I infer the thermistor resistance. From thermistor resistance, I infer temperature. So once I know the resistance, I go to the thermistor data sheet, which gives me a table or a function that plots resistance as a function of temperature. And here is one example here that I took from some data sheet of thermistor resistance versus temperature. So temperature in degrees Celsius on the bottom axis from minus 50 all the way up to 100 degrees Celsius. And then resistance in 100 kiloohms on the left axis, going from essentially 0 up to lots and lots. When I put this thermistor in a voltage divider as the lower leg, so this here is my thermistor down here, and my upper resistance is 100 kiloohms, then, oh, by the way, we choose big resistances in the divider too, so there's very, very small current going through here, so very, very small energy loss through this measurement circuit. So when I do that, so I have that resistance plus the 100 kiloohm, I can evaluate the mathematical expression that computes the voltage input to the analog to digital converter as a function of temperature, again going from about -50 up to about 100 or so degrees Celsius, and we get a function that says measured voltage from 0 to 5 volts corresponds to some temperature. So if I happen to measure 3 volts, I would go across here and go down there and say, oh, that's more or less 20 degrees Celsius, although we could figure it out more accurately than that. This reverse lookup is kind of awkward, so we kind of invert the table and we make a function. So here I'm plotting the curve voltage as a function of temperature. Here I'm plotting temperature as a function of voltage. I just reversed the axes. That's all I did. But now we can see if I measure 3 volts, that's the input to my function. The independent variable, the dependent variable, is the temperature, which again should be somewhere around 20 degrees more or less. I can put this data into a lookup table and use standard lookup table procedures to be able to get a temperature from a voltage. Or sometimes, if you're not super concerned about accuracy, what people do is they draw a straight line and they find the slope and intercept for that straight line and use that to compute an approximate temperature from a voltage. And we could see that, oh, this is linear from about there to there, quite linear. So from about 50 degrees down to about 0 degrees, I'd have quite accurate readings simply by using a linear function. However, if I had cold temperatures, that would not work as well. So that's, again, a design decision you would have to make to decide memory storage and computation complexity trade-off versus accuracy. But that's the basic principle of how you use a thermistor to infer temperature. And then in this topic, the last sensing we look at has to do with measuring battery pack current. We have to measure current to ensure safety. There's current limits on cells generally and on the wiring and electronics in the battery management system. So if there's an abuse condition that the load is drawing too much current or trying to charge too quickly, I need to know that so I can shut the battery pack off. Or to log that something bad has happened for warranty purposes usually, but sometimes diagnostic purposes also. And furthermore, most of the algorithms for controlling the battery pack that estimate state of charge and state of health and so forth need to know what the battery pack current is. There are two approaches that can be used to measure the battery pack current, two electronics types of sensing methods. One of them uses a shunt and the other uses a Hall effect sensor, and we'll describe both of them here. This is a picture of a shunt sensor from our lab. It's basically a high precision calibrated resistor. And in this schematic diagram here we show I've got the battery pack, this is my high voltage set of cells, and my plus minus go to the load, and I've got a battery management system and so forth. The shunt is placed in series with the load. So I've got an enormous cable bolted on there going to the battery pack and another enormous cable going to the load. And all of the load current passes through this resistance. It's a very low resistance, usually on the order of 1/10 of a milliohm. This one here is 1/10 of a milliohm resistor. So that the power lost in the shunt resistor is almost zero. The maximum voltage drop across the resistor is on the order of 50 millivolts maybe. So there's almost no power dissipated, but that voltage drop, that IR drop, is something I can measure with an analog to digital converter, and then I can then infer that the pack current is the voltage drop across the shunt divided by the known resistance of this shunt resistor. So a few comments. The shunt resistor goes into some voltage amplifier. Like I said, it's usually only about 50 millivolts plus or minus that directly comes from the shunt, so I need to amplify that and then measure that with my A to D device and then use that result in the battery management system. You'll notice on the shunt resistor that there are 4 screws, or bolts rather than 2. The minimum requirement would be 2 because I need to put power through this shunt somehow, but I also need to connect a voltage measurement to it. If I were to connect some voltage measurement lead right there and right there, there's a large resistance between that lead and the calibrated part of the resistor. The calibrated part really is from here to here, and all of the connection resistance and so forth can actually be much higher than the 0.1 milliohms of the calibrated part. So there's a voltage drop because of the high current going through here that interferes with my voltage reading because the current carried through here by the load in the battery pack. So instead, I connect my sense leads to here and to here. And my A to D has essentially zero current. It's extremely low current going through these wires to be able to measure the voltage drop. And so there's extremely little IR drop because of the A to D itself when I'm connected here. This is called a Kelvin connection, and anytime we do precision voltage measurements, we use this 4-wire Kelvin connection, and that's absolutely required when you measure something like current through a battery pack. Current shunts have no offset at zero current, so the voltage measured when zero current is flowing through is 0. The offset doesn't change with temperature, and that is a very, very good property. The Hall effect sensor we will see can have a bias or an offset at zero current, and that can be a real problem with some of the battery management algorithms. So if I'm doing something like Coulomb counting, which is integrating current over time to infer a state of charge, then it's important not to have any offset. So the sensor itself has no offset, but the measurement electronics themselves could have offset, so you have to be sure that you are somehow calibrating that out. So that's a positive feature of a current shunt versus a Hall effect sensor. But current shunts are not isolated from the battery pack. This is a 300 volt pack maybe. The battery management system, I didn't mention this is very often powered off of the low voltage bus of the vehicle, like a 12 voltage bus by a lead acid battery. So they're independent power supplies, and there's reasons for that. But won't worry about those here. In any case, this 12 voltage bus needs to be isolated from this 300 voltage bus, otherwise you've got the potential of the 300 volts leaking into the vehicle systems and you touching the door frame and getting zapped with 300 volts. So we need isolation electronics between, well, somehow usually in here, between the shunt and the battery management system itself that ensures that none of that 300 volts has any way of getting back onto the 12 voltage bus of the car. So that requires extra circuitry, which adds expense. There is some change in the shunt resistance with temperature, but we can measure that and calibrate that. We just have to know to do it. And the shunt itself has some energy losses and generates heat that we have to consider when we're designing our thermal management system. I need some way of dissipating whatever heat might be generated across the shunt. And the shunt has a tiny voltage signal that has to be amplified, and so the wiring must be protected from electromagnetic interference. So those are some design considerations. The other type of current sensor that is commonly used is a Hall effect sensor, and here's a picture of one from our lab. And the idea is, instead of having a direct electrical connection to the high voltage, high power lines, I instead pass the line through a coil. And so schematically we see it drawn like this, where the high power line goes through the coil. Physically, the wire goes through that opening right there, and there's a coil wrapped around the wire. And based on Maxwell's laws, if current passes through a coil, it induces a magnetic field, and that can induce another current, and I can measure that current. And by measuring that current, the secondary current, I can infer what the primary current is. It's basically operating like a transformer, if you will. Nice thing about a Hall effect sensor is that there's no direct electrical connection, so the isolation is done mechanically rather than electronically, and that's a wonderful thing. So I don't need extra circuitry for that. However, it's a magnetic device, and magnetic devices have hysteresis, which means that if I follow one pathway and get one set of measurements, if I reverse the pathway, I won't just reverse the set of measurements, I'll actually have a different set of measurements. And that can be an issue, and this can add an offset or a bias to the measured current, which wreaks havoc with some of the algorithms that we'll talk about. So we have to be able to calibrate that offset out somehow, whether it's done electronically or whether it's done in software. Somehow we have to get rid of that offset. So some of these sensors, not all of them, but some of the sensors come prepackaged with electronic circuitry to help minimize this magnetic hysteresis. But even so, they tend to have this offset. And furthermore, this offset drifts. Changes with temperature makes you think that it's a deterministic change, and that's not it at all. It's actually a drift with an unknown change with temperature. And I've worked with these before where we zeroed the offset at room temperature, so we had it fully calibrated, and then we put the thing into a temperature chamber and changed the temperature, and the reported current changed by between 1 and 2 amps, 1 and 2 amperes. It doesn't maybe seem like a lot. If the peak current of this particular device, I don't remember which one I photographed, it's either 600 or 500 amperes. So 1 amp offset doesn't seem like a lot, but in that time we were using it with an application with a 5 amp hour battery pack. And so if I simply integrated a 1 amp erroneous offset for 1 hour, that would say that would make my state of charge estimates off by 20%, and that's just not allowed. It's just not allowed. So you have to have a way of compensating for the offset and zeroing it out, calibrating it out somehow, some frequent calibration. So in this section of notes, we've looked at some of the most primitive basic sensing requirements necessary and possible. We can measure voltage, we can measure temperature, we can measure current. Fundamentally, that's all we can measure in a battery cell these days, although people are working on sensors that you can actually insert into cells to measure other things, and in the future those might actually be very valuable and present. But at the moment we can just measure these things. And from voltage and temperature and current, we are required to be able to calculate and estimate and infer everything else that needs to be known about the battery pack. And that's really a big focus for the later chapters in the notes. But before we get there, there's other requirements having to do with sensing and control, especially at the high voltage part of the battery pack, and that's what we look at next.